All right. My name is Alex Weaver,
And I'm Kevin Sanchez.
and this is our senior design project on the acoustic and infrared thermal imaging camera. So, our motivation comes from us both being entertainment engineering and design majors. Um, we both love audio, um, and we wanted to kind of create a project that blended other engineering disciplines as well as audio and some visual. And I think this project does that pretty well because it can be used in other fields such as mechanical, civil, aerospace, and electrical engineering. And this is just a picture of me a few years back doing big audio things. And what is an acoustic imaging camera? Here's a picture of a pretty expensive one. It usually costs about a few $1,000s, but we will be attempting to construct one only using less than 1,000. Um, the really cool thing about these types of cameras is that they allow us to see things that we aren't normally able to see, and the fact that we are also using thermal imaging is another type of image that us humans aren't able to see. And this is done by using a method called beamforming, which we are using through a program called Ocular. And the heart and soul of our project is this 16 microphone array in a 4x4 grid with a hole in the center. Costed us about 275 bucks, but seems to be worth it with how well the everything's being recorded and whatnot. Whoops, I keep doing that. And this is the specification sheet, the drawings plus all the numbers. The things that stand out would be the audio that it records, the quality, 192 kilohertz, the resolution 24-bit, and you can achieve all these sample rates. We might not be using the highest one. It also has a threshold of 120 dB per SPL. And what else? The 12 volt power as well. Oh, and the USB Mini B. And then for our visuals, we're using standard USB camera for the. If I go back up, this part, this is what we'll be seeing using the USB standard camera. And then attached alongside with it, we'll have a infrared thermal camera. These both costed us about $200 together around, and also shall be worth it. Here's some specifications for the standard camera, some drawings. The things that stood out to me was all the resolutions it can record in, and we'll be using the MJPEG file, which gets converted into AVI, and then a bunch of other ones. And then all these other numbers are just how it's kind of built, the field of view and whatnot.
Something to consider too is that despite it not saying that it's supported on Mac, it still runs on my PC or like my MacBook and great. And the quality itself is fantastic. A lot of it is already upscaled to 4K, and obviously we should lower it because we don't need that much, and 4K is not a square resolution to match the beamforming of the mic array, which itself is like a grid. So we'll likely go either maybe VGA or HD quality, just to like bring it to a more square resolution, or at least cut the 4K resolution into a square shape.
Makes sense to me. These are the specifications for infrared. I'll talk about it a little bit in a few slides about the I2C digital interface. It's not a USB camera. It will have to be connected through a special cable that I ordered online onto the microcontroller on the mic array. And we'll have to solder some pins onto that to get those to read together. The refresh rate is 64 hertz with the 32 frames per second, and I read online that if you swivel the thermal camera really fast, it kind of has like a little small delay. But that's how the camera reads all the pixels and whatnot. So as long as you turn the camera slowly, you don't see that. Another important thing about this is a 3.3 volt voltage. So when we solder it to the microcontroller, we should not be using the 12 volt because that would probably end up killing the infrared camera. And then the field of view. There was a second camera with a field of view that was about 2 times this, but I don't think it was really needed.
So when we were running our code for or testing the standard camera and our microarray through the MacBook, we were using one of the Python code provided to try and capture from both the specific or from all the channels available on the computer. So it would take my regular microphone from the computer and then the USB microarray and also the standard camera. And when we were running it, we installed all the packages and everything necessary for the code, but we kept getting wheel errors for Pi Audio, which it would install itself when installing through like my normal Mac terminal through Homebrew, but anytime I try to run it, it would say like it's missing the package of the specific Pi Audio itself. So like we had to try and debug that. And we listed what was included in the directories in my computer, which was Mac core, the poor audio, and like another poor audio. So like Pi Audio is also missing, and we would need to install that since it's like not registering as like in my files. So we moved one of the original directory into an older directory or like a separate temporary directory. I ran the install Pi Audio through pip, like pip install Pi Audio, but it would still give me the error. So I changed the command to sudo move because that's more of the Mac command and gave me permissions to do it despite any issues with a previous like mv move command. And then we still had the same issue, like the wheels still weren't constructing despite all this movement and like trying to get any overwritten files like out of there in case like they were overwritten. The next step was to write the export arch flags as an arch x86 underscore 64 because that the computer was reading my Mac as like an older Mac, so Pi Audio itself wasn't allowing the install for itself basically, and I needed it to read my computer as a computer with an x86 architecture, so that's what that command did. I then showed the list for the user's local include that had the previous top 3 files, but now they were gone. So I was able to move the previous files back out and reinstall the Pi Audio file, and this time it did install, which allowed us to finally be able to use the code that allowed us to record from the microarray and from the standard camera. And in these videos, so the left one's our demonstration video real quick about how the microphone array sounds just through like OBS software, because I wanted to see like the difference between what the Python code sounded and like looked like compared to like just a regular standard recording. Because through OBS, I think we can separate the audio tracks and the video track like with it separate from each other, and we could probably synchronize them and avoid like the steps through Python if necessary, as it would like really reduce the workload for us and hopefully like get them working as soon as possible, or like give us another option if the Python code we can't get like the fixes or we're just having too many issues with that. And in the demonstrations folder, that one has of our file test for that went through the Python code. So it has an AVI and a wave for the audio. The problem with the audio for like the Python recordings is that it's really quiet, and despite like going on max volume, it's still very like shallow. You can barely hear what we're saying or like any of the background. While in the OBS software, about halfway volume is still pretty. It's still audible. It's pretty audible, which I guess goes to show that there are still some issues we have to resolve through the Python code. And also, if when recording through the standard camera with the Python code, sometimes buffering might cause issues where it looks like we're recording in slow motion, then instantly picks up speed to double, quadruple the speed, and then goes back to slow motion, trying to keep up or like keep pace with the recording basically. And maybe this might be caused by buffering from the computer itself. So we can definitely test this on a more powerful computer. But right now, at the moment, we weren't able to get it installed on like the library computer for Mac, or as it crashes the Windows still. And yeah, we'll embed our presentation, this video, into this file space. And yeah.
And then this is our flowchart. Basically, in the progress report, I colored in what we have completed and what we still need to do, but basically the hardware, the USB camera, and the thermal camera will kind of be right here. The thermal camera would be pointing into the NanoShark controller, and then they all go to the computer. And then, so these are all checked off. We're all good to go on hardware, except for the thermal camera, obviously. And then software, well, this is just a given sound signal. Ocular beamforming, don't have it coded quite yet. This would just be Python again up here. I just put Jupyter because in the beginning of the project we thought we would be using a different one. And then these would be the two that we're kind of aiming for over the summer / into EE498, using the code to get the two signals together and then to display it in real time. And then basically kind of the same thing I just went through. We're good on audio and video capturing. We have captured them, just not in the most ideal fashion, which leads to this one. Acceptable meaning our frame rate is consistent on the video and our levels on the sound from the microphone is good to go. And beamforming and visualizing it, all that towards the end. And then once we know that the project is good to go, there's some secondary things that we'd like to do. Potentially 3D print a housing hardware for the cameras and the microphone, just to kind of not let it just kind of be hanging out there with all its parts showing, and make it kind of look nice and whatnot. The thermal imaging camera coinciding with the USB camera, haven't quite decided how we want to do that. If we want the thermal imaging camera to go above the USB camera or behind it, like a 180 degree. And then lastly, rotating the system, the whole tripod and microphone and camera whole system with a servo motor. And then also kind of what I just said, these three things basically in different wording. And then here's kind of our timeline for what we kind of hope. Early December, have it ready for presentation. Somewhere in October, have it fully built and kind of starting to be tested for optimal use. And then the AV processing, all the problems we mentioned earlier with the low volume and all that, hopefully late May, early June. The thermal camera installed over the summer, and then 3D printing and having everything come together around mid to late summer. And yeah, if you want to add anything, Kevin.
No, I think we're good. I think, yeah, we covered most of it. And yeah, we just hope to get a lot of the work done over the summer. We've had a lot of projects mostly preventing us from truly dedicating a lot of our time. So yeah, we hope to get through just the coding process, and everything else should fall into place once we get the audio and visual processing done.
Yep. All right. Thank you.